All right. I hope everyone has a good weekend. So today we're going to talk about oxidation reduction, redox, as it applies to environmental circumstances. And as I kind of alluded to already, one of the key things that is very important and wrapped up in this is photosynthesis, respiration, production of oxygen, consumption of oxygen. So associated with this, there was a topic video that's just a review of redox. There's some slides in here that basically say, see the review video. I sent you guys an email about that before. If you haven't looked at it yet, you should look at it. It should be stuff that you know, but I'm going to go over the slides here. I'm not going to talk about them in class. So they anticipate that you already know something, remember something about oxidation reduction. Just a final reminder, I won't be here next Thursday or the following week. All three of those lectures, again, as communicated multiple times by email, will be remote learning lectures. Watch them, do the work, ask me questions if you have them, because you will be responsible for the content. I'll also be assigning the first homework assignment during that time. So there's new reading for this week. It includes chapter 3 and part of chapter 5 today. And then next time it will be chapters 5 and a very small part of chapter 21, which is on environmental microbiology, specifically with respect to oxidation and reduction, which is what we're going to be the topic of Thursday's discussion. So just as a reminder, photosynthesis and respiration is this competing reaction that happens in the environment all over the place on Earth in different proportions and in different balances. It basically takes water and carbon dioxide to make generic carbohydrates and oxygen. Okay, and that direction is photosynthesis. Written in the reverse direction, what we do, we take oxygen and we burn carbohydrate to make carbon dioxide and water. But I want you to emphasize that what I've highlighted here in the colors is that here we're taking oxidized carbon in the presence of reduced oxygen and making reduced carbon and oxidized oxygen. Hopefully those terms are familiar with you. Oxidation and reduction is a very important process. Oxidation is the process of losing electrons, and reduction is the process of gaining electrons. So why is this important? It's important because the presence or absence of oxygen and the degree to which oxygen is present either at saturation with what we have in our atmosphere or some lower value, or when we get to the point of anoxia where there's no oxygen, we can take other equations. Nothing does this per se, but there's other things that do this. They just use something other than oxygen. And in so doing, they make the environment more reduced. Okay, and we define how oxidized or reduced something is with a parameter called PE. It's defined directly analogous to pH, and we will talk about it in a few slides. So in waters that have a lot of what we call primary productivity or photosynthesis, we have an oxidized situation. Going to be something that has a high PE. In cases where we have a lot of respiration, I've talked about this before already, places where there's no light, places that are isolated from exchange with the atmosphere, in, for instance, soils or bottom waters or various other settings, groundwater, for instance, then when we go back in this direction, we go to what's called a low PE setting. Settings where respiration is dominant, have less oxygen. And there are a lot of chemicals in the periodic chart that change their behaviors as a function of what the PE is. There are also organic molecules that change how they break down, what they break down into, especially when they're being broken down by microorganisms as a function of what the PE is. So we have to understand PE first before we can understand the environments in which we find chemicals. So I'd like you to think about, maybe you've thought about this before already, but photosynthesis and respiration is basically this exchange of electrons and oxygen between chemicals. And it's important to recognize that what we do when we're doing respiration is take oxygen and reduce it so that we can liberate energy from carbohydrates. And so if you take a step back and recognize that there are other metabolic strategies that organisms can use, especially single cellular organisms, where they take something other than oxygen to play that same role, then you can start to see that there is a much greater potential for diversity of life, not only on this planet, but on other planets where there may not be oxidizing environments in the atmosphere. So what drives this process, the process of respiration, whether it's aerobic or anaerobic, is the presence of organic matter. Now on this planet, the presence of organic matter is largely, not entirely, but largely related to photosynthesis producing it. You have some non-biological phenomena that can also make organic matter, but not very much of it. So it's a two-handed sort of situation where unless you have organic matter present, which requires organisms, then you're not going to have respiring organisms that consume that for energy. You kind of need both of these things together. Okay, so as we've talked about now a couple times, to support photosynthesis, that what we call primary productivity in the presence of light. We need light, we need carbon, we need nutrients. It's pretty much always carbon in any environment that we look at, with perhaps the exception of the very, very deep subsurface biosphere, which might be carbon limited. You know, but that's a different kind of life anyway. It doesn't depend on light, it depends on chemicals. And we'll talk about chemosynthesis later. So in surface waters on the planet that are in exchange with the atmosphere, there's always plenty of carbon, just through the dissolution of carbon dioxide into water to make bicarbonate. There is or isn't light as a function of things like how particle rich is the water, how deep in the water are we, are there other components of the water that absorb light or make it cloudy, those kinds of things. And then these things, the nutrients, become sort of the limiting factor for photosynthesis. The primary nutrients being nitrogen and phosphorus, and there's a whole bunch of micronutrients that we'll talk about, some of them not very soluble in water, things like iron. So we're going to have a whole topic where we just talk about photosynthesis. So I'm not going to go into details of it now, but I want you to kind of get the feeling that every place you are, whether you're in water or you're in a terrestrial ecosystem, like here on the surface of the Earth, if there's plants, there's production of oxygen. If there's production of oxygen, that means photosynthesis was operating, and we were therefore in an oxidized environment. Okay. Now, another important thing is that our atmosphere is really well mixed for oxygen in the troposphere, meaning it's really hard to find variations in oxygen concentration at a measurable level. So wherever the oxygen is being produced, you know, tropical rainforest, surfaces of the oceans in the high productivity zones, it's managing to get into the atmosphere and kind of mix it everywhere. So it doesn't matter if you're at the pole where there's very little photosynthesis going on, you have an oxidized environment. Now, the presence of oxygen, which is, as I say, an oxidizing agent at a high abundance, at a relatively constant concentration, buffers the environment. In redox buffering, we use a different term, we call it poising, but it means the same thing. If you think back to acids and bases and say, oh, well, there's a certain acid conjugate base pair and a certain ratio and concentration that's setting the pH so that you can add a little bit of hydrogen or hydroxide and the pH doesn't change. That's buffered. In the case of the surface of the Earth, where we have photosynthesis, the presence of oxygen is poisoning the system at a certain value of pH. And importantly, that is happening by the competing and collective cumulative action of the photoautotrophs, the photosynthesizing organisms, and the heterotrophs, the respiring organisms, such as ourselves. So aerobic respiration, just some terms, right? This is respiration that involves the consumption of oxygen. To use oxygen as an electron receptor, itself being an oxidizing agent of organic matter to liberate energy. Anaerobic respiration exists in places where there isn't any free oxygen. There are other molecules that other organisms, usually consortia of microorganisms, use to do the same process. They consume organic matter, they liberate energy from it, they just use something else as their electron receptor. We'll see what that list is later today. Question? Oh, no. So this is a start of the series of slides that are reviewed in that topic video that if you haven't looked at, please look at yet. And rather than put it up as an MP4, I just put it onto YouTube. So I should have changed that note in red from last year. I sent you the link and you can find it on La Lima in the topic video section. But I just want to remind you what oxidation state is, right? It's the charge on a material that whether we're looking at an individual ion or a compound ion, we look at the arithmetic sum of all of the individual atoms in there, and their sum has to equal the charge on the material. It's like a +3 ion or -1 ion as a compound ion. And we partition these up using various rules. And the reason we want to know the rules is so that we can look at the flow of electrons. So that when we have chemical equations where electrons are being transferred, it's not enough to balance them for material. We also have to make sure they're balanced as written for electrons. And when we do that, we can use the thermodynamics to derive parameters like the electromotive force, which is what is converted into the environmental parameter PE. So all the slides that have this on the bottom, which are how do you calculate oxidation state, some examples, sodium chloride oxidation state, NO oxidation state, a chemical reaction between a reduced and an oxidized form of nitrogen and an oxidized and a reduced form of chlorine, how we do the accounting, how we balance it, the definition of oxidation and reduction and splitting reactions into half reactions, the half reactions for that reaction I just showed you, and the Nernst equation, which is something that you probably learned at some point. You're solving equations with batteries. So you want to remind yourself of what the delta E electromotive force is, how it relates to E naught, the standard state value, what 0.059 refers to as the combination of several different constants at 298K. So if you're solving problems not at 298K, you can't use this equation. You have to substitute in a different temperature. And being the number of electrons that transferred, and you log K, the equilibrium constant. So I just want to emphasize for you something I've said before already, that when we write out chemical reactions, what we're really writing, when we write the expression of the products over the reactants, is something called Q. It's a reaction coefficient. This special case where the proportion of the chemicals that go in here are exactly what is predicted at chemical equilibrium makes that ratio into something called K, the equilibrium constant. But you can have any mixture of materials in the environment because there's multiple competing equilibria and non-equilibrium situations. So that in a more general sense, Q is what defines every mixture of chemicals that are related by a chemical reaction, and K represents a special case for chemical equilibrium. And part of the reason this is important is that when we're at chemical equilibrium with a lot of thermodynamic parameters, these values go to 0, and then we're only looking at the standard state values. Okay, so here's some other relationships that will be useful, for instance, relating the electromotive force back to the Gibbs free energy, which is hopefully something you remember as being related directly to the equilibrium constant. Delta G naught equals minus RT, natural log of K, R being the universal gas constant. Or you can write it with regular log units and put that 2.3 in there. That's the conversion between natural logs and logs. The other kind of important things I want you to recognize is that there's this parameter, PE. It's basically just a minus log of the electron activity in the environment. I'll define that for you a little bit better in a second. But we can use two different ways to express how oxidized or reduced an environment is, and that's shown here in this bottom expression. We can do it with something called PE, or we can stick with E. And the reason I bring this up is because you will find diagrams in a lot of textbooks that use one or the other, sometimes both. And the important thing about PE and E is that they're related together simply by a constant, 1 over 0.059, which is the same 0.059 that's in the Nernst equation. So if you're given one and you need to get the other, it's a pretty straightforward thing to go back. Okay, so the last thing I have in here is in the review stuff is a little bit about how you use the Nernst equation to calculate things like electromotive forces. And it's important to recognize that by convention, all around the world in chemistry, we compare other half reactions to this reaction where hydrogen is gaining electrons, it's being reduced to make hydrogen gas, given a value of E of 0. This is something that's called the SHO or SHE, standard hydrogen electrode, or standard hydrogen oxidation. It can be written in either direction, but when you look up other numbers in a table, they are written given relative to a value of this being 0. So it's a reference value. It also means that when you find reactants that are written where the E naught is positive relative to this, and it takes less electromotive force to make that oxidation or reduction happen, and when you have a negative value, it takes more, right? And so we can start to think about environments that are so reducing where hydrogen ions can make hydrogen gas, things that are negative with their E naught relative to this are going to take more electrons. Those tend to be not existent in the surface of the Earth. Those are interior of the Earth kind of values. This ends up being kind of a lower limit of how reduced our environment can get, because if it gets any lower than this, then water itself doesn't exist. Water basically contains hydrogen ions that would be decomposed. Okay, so now that's the review stuff. And like I say, if anything that I just said was hazy, please look at that video. So now I want to talk about this concept of PE. PE is the minus the log of the electron activity or concentration in a setting. You might say, well, where do I get that from? You get that from the half reaction. Just like you write out an acid-base half reaction where you've got some acid reacting to make a proton and a conjugate base. We put the protons into that equation. You know, they don't really exist as free protons in solution. And we can take the minus log of both sides and rearrange to get pH, which is the minus log of the hydrogen ion concentration. You do the same thing with a half reaction, and we're putting in the minus log of the electrons. We're leaving them in our expression, taking the rearranging stuff, and we come up with this value of PE. So it's an important variable, just like pH, and we're going to look at PE, pH diagrams as important phase diagrams to understand the environmental conditions in one place or another. And as I mentioned before, the analogy to buffering in a pH system is called poising in a redox system, and that's when something is setting the value of PE, right? And this basically just explains how poising is similar to pH and how PE is defined analogously, to pH. Both of these things are conceptual, but they're useful. We understand the difference between an acidic and a basic environment. We should understand the difference between an oxidizing and a reducing environment. That's what we're talking about with PE. So with pH, most people have an intuitive feeling when pH is high, it's basic, meaning there's very little of this around. And when pH is low, it's acidic, meaning there's a lot of this around. It's the same thing with PE. When PE is high, it's an oxidizing environment because there's very little free electrons around. And when PE is low, it's a reducing environment because there's a lot of these things around. The only difference between PE and pH is that whereas pH is at 25 degrees C or 298 K is a fairly constant set of parameters that set it. So the values that we typically deal with go between 0 and 14. PE is a little bit more complicated in the sense that what the number we calculate for it depends a little bit on what the pH is. So the ranges in the environment can shift from place to place. There's pH 7 range, there's a pH kind of 1 to 3 range, there's a high pH range, and it moves to different values, although the range itself doesn't change. So both these things are conceptual, but they're things that we can measure. Okay, and that's the important thing for our purposes, because as I say, as a function of both of these two things, most other chemicals we confront in the environment behave differently depending on what the conditions are. Okay, so I'll give you an example now of a reaction, iron 3 going to iron 2, reacting with hydrogen, going to hydrogen plus. As written for iron, is that an oxidation or is that a reduction? What happens in oxidation? Right. Reduction, gain electrons is reduction, lose electrons is an oxidation. Hydrogen is being oxidized, right? Because it's going to H plus. And that's just that part of that reaction when we divide it up into half reactions. That's just a standard hydrogen electrode, which we can look up in the table, has a value of 0. But that other half reaction, we can also look up in the table and see it has a value of 0.77. Right? So I can write an equilibrium expression for that upper half reaction, the one related to iron, right here. I put my electrons in there, right? And I can rearrange it where I put the electrons on one side of the equation, the equilibrium constant, and this ratio, which in an acid-base equation, that would be the equivalent of the conjugate base and the acid pair. In this case, it's the conjugate pair of reduced and oxidized form of the chemical. And take the minus log of both sides, right? So the minus log of this, minus log of this, minus log of that, this just becomes PE, okay? PE naught, the standard state value when we are at chemical equilibrium, is just the minus log of 1 over the equilibrium constant. And we're still left with this equation minus log Fe2 plus over Fe3 plus. So in a more general form, because there's only one electron transferred in this equation, we don't get to see the N that we would see in the Nernst equation, right? So if we generalize this equation for cases where there's more than one electron being transferred, then we just have PE equals PE naught minus 1 over N, however many electrons being transferred, the log of the reduced over the oxidized form, or more commonly written where we flip the direction of the half reaction and is PE equals PE naught plus 1 over N log oxidized over reduced. So by flipping these two things, we just flip the sign. And that's just algebra of logs. Okay, so that's how we get PE. That's an example. The rest of the time, we're going to use PE to understand it as an environmental parameter. And the first thing we want to think about is how do we set some understanding of the limits of how oxidized and reduced things are on Earth from some of the major materials that poise the system. And besides oxygen, poising the concentration of oxygen in the atmosphere and water is in equilibrium with them, another kind of critical thing is the presence or absence of water. Turns out that if the environment were very oxidizing, water would decompose to oxygen, and that's what the E naught and the PE values are. So if you imagine there would have to be some other thing that was producing oxygen besides photosynthesis on Earth, and there's no other planetary body we know of in this solar system or another with a more oxidizing environment than us. So it's very unusual to find, naturally speaking, this reaction happening. It can happen in the lab. We do it all the time when we want to make oxidized chemicals. But in nature, the very presence of water limits how oxidized the environment is to values below this. Does that make sense? That's poison. Just having water present. If somehow all the water were consumed, then we might be able to go to higher values. But we don't have very many chemical reactions that can naturally do oxidation. And so photosynthesis is one of the primary ones. There's also a reducing limit, meaning if the planet, parts of the planet get so reduced that water itself decomposes, if it consumes electrons and makes hydrogen plus hydroxide, then we don't have water present anymore, not in its standard form, it's in hydroxide form. This happens in the interior of the Earth, in the mantle, in the core, etc. But at the surface of the Earth, we tend to not find conditions more reducing than this. Again, we can do it in the lab, no problem. But naturally speaking, if we have water present, we're stuck between a PE value of 20.75, this happens to be at pH 7, and this equation, which boils down to the standard hydrogen electrode when we rearrange it a little bit, which we already know by definition has a E naught of 0 which again is a PE of 0 because they're just related by 1 over 0.059. So these two values represent a limit, and we can look at sublimits within them, but I want to show you first how we do this on a diagram. We can take that equation for that first one, the oxidation of water to make oxygen. We can apply the Nernst equation to it and do some algebra and come up with an expression that says E equals E naught minus 0.059 pH, which can be written rearranged by substituting in the E naught value from the prior slide to E equals 0.05 minus 0.059 plus 1.23 volts, or if we convert it into PE by taking the minus log of both sides, PE equals pH plus 20.75. So that's just an equation. It's going to turn out to be the equation of a line y equals mx plus b, and we're going to see that the other equation that I just gave you for reduction of water to hydrogen does the same thing. There's one little detail down here, which is that when I solve this equation up here, I put in a partial pressure of oxygen in the atmosphere of 1. That's like, that would mean 100% of our atmosphere is oxygen, which doesn't happen. We know that it's more like 20%. So I can go back here and redo this whole equation where I put in 0.2 instead of 1 over here. And it only changes this to 1.22 from 1.23. So it's a small difference, and you will see this written two different ways. Different diagrams will plot this line up with a slightly different intercept. So it's in that 100th place. So just so you know, that's a subtle little detail. Now we can do the same exact thing for that reducing limit of water, apply the Nernst equation to the reaction of H2O going to make H2 by decomposing by being two kind of reducing of the environment. Make the same assumption, which is that the partial pressure of hydrogen in the atmosphere is 1. It's an upper limit. Obviously, the planet can't have more gas than that in its atmosphere. The partial pressure or the total pressure is related to the mass of the planet. It can obviously have less, but that's the maximum reducing value we could get in our atmosphere. Plug in our numbers and we come up with an even simpler expression, E equals minus 0.059 pH plus 0, or PE equals minus pH. So you can already kind of see that this PE equals minus pH. If we look at this in PE space, the slope is -1. In this case, the intercept is 0. If we go back over here, again, the slope is -1 and the intercept is 20.75, or a slightly lower value if we use this one. So those are two parallel lines. Parallel because they have the same slope. The reason they have the same slope is because they have the same numbers of electrons being transferred relative to the number of protons being transferred, right? And I've just kind of written here how we express these as lines. The next thing we're going to do is look at these together on a diagram. A diagram called either, some people call them EH-PH diagrams, some people call them PE-PH diagrams. I always learned them as PE-PH diagram, but it's just a question of whether you're plotting this value or that value, again, them being related together by a constant of 0.059. So this is a depiction of that lower line, and that's a depiction of that upper line. And that field that I've highlighted in blue is the field where water can exist. And if we get too reducing, like in the interior of the Earth, we don't have free water anymore. And if we somehow got too oxidizing, then we wouldn't have water anymore. But just by having water, we know that we're in a box with a certain set of values, right? That at pH 7, we calculated pH 7 being somewhere up in the middle, 0 and something like 20.75. And as I was mentioning before, as the pH changes, the upper and lower limit absolute values change, but their offset doesn't change because these two lines are parallel to each other. So this is the same diagram with some values on it. This one happens to be an EH-PH diagram. And you can see off to the side, there's a table, or not table, on the diagram is a field that shows you some specific environments on the planet. I have that blown up on the next slide, but I just want you to start to think about what are the ways in which we could go down in PE and they are isolating ourselves from the main source of oxygen, the main source of oxygen being the atmosphere and or photosynthesis. So whether we're in a body of water, open body of water like a lake or the ocean, whether we're in groundwater, whether we're in soils, as we move away from the atmosphere, we tend to migrate down in this diagram. And it's not just by happenstance, it's because in all those environments, there's respiration going on, that thing we started the discussion on today. And respiration consumes oxygen, and when we consume oxygen, our PE goes down. So this, oh, excuse me, this is that same diagram blown up again. Again, the lower and upper stability limits. And what you can see is a couple of things. For instance, contact with the atmosphere. This is graphical, right? These numbers would be right up there by the line. But you can see there, mine water, rain, streams, ocean. What all those things share is a high PE, but different pHs. The oceans are basic. Streams are closer to neutral. Rain is more acidic, because of the dissolution of carbon dioxide, like we talked about last week. And the transition from here to here has to do with the consumption of hydrogen ions and the weathering of silicate rocks. This is largely affected by the calcium carbonate cycle associated with photosynthesis and respiration in the water column. Mine water is something we haven't talked about yet, but we will get to it. It's commonly very acidic because the oxidation of reduced iron and reduced sulfur will produce some extra hydrogen ions. But so these settings here are all in equilibrium with the atmosphere, so they have atmospheric oxygen and just different pH values. But when we come down here, we can see transitional environments, bog water, groundwater, things that are isolated from the atmosphere, like organic, rich, marine, saline, saturated soils, xenic, marine. If you recall, last time we talked about eutrophic lakes, they would be down here. And so the process of isolating from the atmosphere and consuming organic matter is what pulls us down. It's a function of the extent to which it happens, combined with the extent to which we can replenish oxygen, even if only partially, by things like diffusion or advection, flow of water, other kinds of disruptions, which can help oxygen kind of penetrate down into the environment and keep these things from going super reducing in some cases. Okay, so this is just how we calculate the oxidizing limit for water. That upper line is a function of different pHs. We can plug in different pH values into that equation that I showed you before and get some reference numbers, which, for instance, tell us what the E0 values are going to be as a function of changing the pH. It's not important to know what these numbers are. You can just read them off the diagram, but just to get a feeling for how much it varies as a function of varying the pH. It does vary a little bit. Okay, so what we're really interested in, obviously water is super important, we all love it, but how about all the other chemicals in the periodic chart? Which are the ones that matter? And we can make phase diagrams where we take that parallelogram for water and we say, all right, let's look at something else that we know is oxidation reduction sensitive, like carbon that goes between CO2 and methane, or sulfur, which goes between sulfate and sulfide, or iron, which goes between ferric and ferrous forms, nitrogen, the list goes on, but we'll look at a handful of them. And we're going to draw up the same diagram, always going to have that same parallelogram for water on it. We're going to put some other lines on it. The important thing to remember about lines on phase diagrams, chemical phase diagrams, is that when you're on the line, the concentration of the things that are related by chemical equilibrium have equal activities. Activity is a slightly more sophisticated way of describing concentration. In cases where we have very unusual solutions, sometimes the activity or the apparent concentration is different than the real concentration. Think about really salty water, for instance. Some of our anions and cations don't behave like they're present because they're doing other things interacting with each other. So I commonly use the term activity, but for the sake of argument, you can just think of it as concentration. Or if you were in the gas phase, it would obviously be a partial pressure. So we can solve equations using the Nernst equation, writing out half reaction lines, just like we did for the reaction lines of water. But how we set that, where the line is making this assumption that the things that are related in equilibrium constant have equal activities. So let's look at all the chemical reactions that we can think of, inorganic ones, for the two most common forms of sulfur that we find in the hydrosphere, which are oxidized sulfur in the sulfate form and reduced sulfur in the sulfite form. So there's basically two sets of reactions here. These first two are the dissociation of a diprotic acid, sulfuric acid, to make HSO4 minus, and then HSO4 minus dissociating to make SO4 2 minus. And the equilibrium constants for those two things are there. Then you'll see the one distinction here, that log K, which is just the log of the equilibrium constant, is minus 1.98, and this log K is plus 1.98. So interestingly enough, because when we draw pH diagrams, we tend to cut them off at pH 0. This chemical reaction happens at a pH of about -2. It's that acidic. You go and buy a bottle of H2SO4 over at chem stores, and it's pretty much entirely dissociated to this and this, right? And this happens at a very low pH. So in fact, it being a very strong acid, even this stuff is pretty much dissociated to this and this. But the important thing to note is that on the standard PE-pH diagram, things with log K's that are positive won't even show up because they're going to be in negative pH space. Now you'll get hydrogen sulfide, it's two dissociations, right? It's chemically analogous to water. And so you can see here, this is a much weaker acid, right? This happens much less than this. That's 9 orders of magnitude. That's 1 billion times less likely to dissociate. So if you were to buy yourself some hydrogen sulfide, which comes typically as a gas, very little of it would be dissociated to this. Most of it would still be in this form. It also has a second acid dissociation, which makes sulfide. Now, interestingly enough, we know we have sulfide minerals in nature, right? We have things like pyrite, galena. And so somewhere on the planet, we make this stuff, right? So somewhere it gets reducing enough where enough of this hydrogen sulfide forms this stuff so that, you know, we know that, those kinds of PE values associated with a log K of -12 or -13 exist somewhere. Now, the other important thing to note, oxidized form of sulfur, reduced form of sulfur, is that these things are related together by chemical equilibrium with an equilibrium constant. And that equilibrium constant is hugely dependent on the oxidation state of the environment, right? Sulfate consumes hydrogen ions, right? So it acts like a base. It also consumes electrons, right? So it's an electron receptor. It acts like an oxidizing agent to make sulfide and water. So you can think about this different ways. You can say, well, sulfur is being reduced, but it's also, sulfur is, basically oxidizing hydrogen, right? It's taking these hydrogens and converting them into water. And that has an equilibrium constant. The only reason I say that is because we're going to plot all these things on that PE-pH diagram so you can see how we can depict sulfur that way. So the first thing to do is to look at the acid base, the first set of 4 equations without the oxidation reduction. Here's the standard PE-pH diagram. Here's the lines for these acid dissociations. And as I said, that first acid dissociation, this guy, happens at negative pH space, so we don't get to see it on the diagram, right? It would happen somewhere out off to the side. This equation, the second acid dissociation, shows up as a vertical line. The reason it shows up as a vertical line at a specific pH is that regardless of the PE, because there's no electrons involved in that equation, it's always going to have a value that is associated with the pKa. There are no electron transfers in this reaction. And the two hydrogen sulfide dissociation reactions show up here as 2 other vertical lines. So we end up with a diagram that's got 3 vertical lines for the acid-base chemistry. Now we're going to get to what happens with the redox, but when we get to the redox, you'll see that those vertical lines are still present, but only as sub-line segments, because in certain parts of the diagram, they can't exist. So this is the full diagram again with PE and pH. This equation can be plotted up here as this line, okay? And so that line on this diagram separates the field of oxidized sulfur from the field of reduced sulfur. It's pretty far down, pretty far down, close to the water stability line, water converting into hydrogen, which is what this lower line is. That upper line is water oxidizing to oxygen. So this already tells us that the environments that have gotten to the point where somehow sulfate can be converted to sulfide are pretty reducing. They are very isolated from the atmosphere. Therefore, when we find sulfide-bearing minerals, we know that the assemblage of conditions were very reducing. Now, I should also note that when we make these diagrams, we're assuming 298K. If you were solving problems, for instance, with metamorphic petrology or some other condition that has very different pressure and temperature space, we'd have to look up different numbers for these equilibrium. Or there are calculations you can make that approximate what the effective temperature and pressure is on things like delta H and delta G and delta E. But for now, we're just doing 25 degrees C things. So this H2SO4 or HSO4 minus going to SO4 2 minus, that chemical reaction line stops when the sulfur goes from oxidized to reduced. It doesn't continue down here because it doesn't exist anymore. Just like the two vertical lines that we showed on the last slide, they only exist in this lower field because once we jump up into the field where sulfide can no longer exist because it's being oxidized to sulfate, they get cut off. Does that make sense to everyone? Okay. So the other thing to remember is that every place on these lines, we can calculate that whatever the chemical reaction was, we have to look up what we wrote. But for instance, on this line, this reaction applies. It means we have unit activity, okay, of the reactions, of the reactants and the products relative to their stoichiometry, right? So we're always going to have 8 times as many hydrogen ions as sulfate ions, but on this line at a given PE and pH, the relative proportion of sulfate and sulfide are going to be equal to each other. Okay, so here's another set of diagrams. This is for iron. There's 2 forms of iron. This one is the most common form of iron in the environment, including the effect of solubility. And this is the most common kind of iron as a function of PE and pH that is dissolved in water. So let's talk about this one first. This diagram is calculated. It's got the lower and upper limits of water on there. And you can see there that the iron 3+ field is way up there in the top, Fe3+. And down here, we've got Fe2+, dissolved in water as ferric and ferrous iron. And as soon as we hit that red line, we have hematite, which is a solid mineral, or magnetite, which is another solid mineral, and water. So that we anticipate, unless there's something added to our solution that can increase solubility. Does anyone remember what kind of thing can increase solubility of metals, transition metals? Chelating agents, dissolved organic carbon, right? So we throw that in, this diagram is going to change. This is assumed for pure water, right? We reach a certain solubility limit. And that solubility limit is pH limited and PE limited. We need to be in acidic environments to have dissolved iron if we don't have organic. That's what this diagram is telling us. But it will also tell us at what place does it change from being oxidized to reduced. Now, there's one other tiny little detail, but you got to look down here to like the 0.1 font. This is calculated for a concentration, total activity of dissolved species is 10 to the minus 6, right? There's a certain amount of iron that we can stick into solution. If we change the calculation that was used to make each of these lines to change the activity to 10 to the minus 4, we go from the red line to the purple line, which is telling us that the boundaries that we see on these diagrams are very specific to the conditions they were calculated for. You cannot simply assume if you find a diagram in a book, like when you're solving a homework problem, that the lines on the diagram apply to your circumstance. They apply to your circumstance when your circumstance is the same as the ones that it was calculated for. It's also important to recognize that every line on this diagram is just an expression of the Nernst equation, which you can always write out. And then you can solve for, and you don't even need the diagram. The diagram, we use them as guides. You pick it out of a book really quickly and say, oh my gosh, how does cadmium behave? Because I don't have that memorized. Or how does uranium behave? Because I don't have it memorized. And you can kind of see, okay, based on the PE and the pH, where approximately it's going to be. So another thing that's kind of interesting to note is that there's this iron has this kind of unusual chemistry where when it's dissolved in solution, the field that separates truly dissolved oxidized iron from reduced iron tends to have a change at a very high PE, but when we go into the solid forms, the transition happens from oxidized to reduced at a much lower PE. This is kind of an artifact of the kinetics of how things work, and that's why it's useful to look at this diagram instead, which is the form of the iron in water, even if it isn't the dominant form. Even though we know over here we got a bunch of solids, there's a little bit of iron in solution based on the solubilities of these two materials, and we can see more clearly how iron is changing as a function of both pH and PE. And so we have a series of lines and a series of diagrams. You can see there A, B, and C. I'm going to show you the equations for each of those three lines on the next slide. You could calculate the lines for any one of these other ones in the same fashion, but notice that B is a vertical line. Things that are vertical are acid-base transitions that don't have any impact of PE or electron transfer because they're not electron transfer reactions. So every one of these vertical lines is an acid-base reaction. Flat lines, like line A, that is a reaction where only electrons are being transferred and there's no effective pH. And anything that isn't vertical or horizontal is changing both electrons and hydrogen. Okay, so I'm not going to try to talk through each one of these things, but line A is the reduction of iron 3. Line B is the reduction of iron 3 to FeOH2+, it's a compound ion. And line C is the taking of Fe2+ plus water to make FeOH2. And this reaction involves electrons and hydrogen ions. You can see this written here, so it's not going to have a slope that's either horizontal or vertical. But these are three equations that can be rearranged into the units of, either EH versus pH, or take the minus log of both sides and you can write them in PE versus pH. Just depends on what kind of diagram you're putting them on. Okay, so now let's make life a little bit more complicated, meaning a little bit more realistic, and say, all right, we got an environment, we got some iron, we got some water, total concentration is 10 to the minus 6, which is the red thing, 10 to the minus 4 is that one. And let's take this concentration at 10 to the minus 6 and let's add in a little bit of sulfur and let's add in a little bit of carbon. And again, you got to go down here into the details. You can see that the total amount of sulfide is 10 to the minus 6, and the total amount of carbon is 10 to the plus 6. And what you see is that the diagram looks exactly the same, except for right down here in this area, not too far off of neutral pH, up to values of about 8 and down to values of about 6. And at very reduced values of PE, meaning close to this green line, we have two new fields added in there. We have the field of pyrite, we have the field of siderite. Siderite is iron carbonate. Now, this is in the absence of any other things, where we could add some manganese and various other transition metals. And when we add more stuff to the diagram, things get complicated because the fields move around because chemicals are competing with each other. But we can see the effect of adding sulfur. If we were to add more sulfur, this pyrite field would expand. If we had less sulfur, the pyrite field would contract. And you can see that already now we can go into environments such as paleosols, and if we find pyrite and or siderite present, that's telling us that that paleosol or that paleosediment, whatever it is, formed at a condition that was very reducing, close to the line that separates hematite from magnetite, or if you go back a few slides ago, close to this line here, which divides sulfate from sulfide. You can't make pyrite, for instance, until you make sulfide. So you already have the iron 2 present, because the iron transition happens higher up, but you can't make pyrite until you also make sulfide. So here's some other diagrams. Again, EH in this case and PE, both of them being shown to you, related by a constant, versus pH. This is water. This is nitrogen in water. Nitrogen has this primary form of N2, which is very stable in most oxidation reduction settings, And so it dominates the field. When you get right down near the bottom, you can have some ammonium or ammonia, which is a pH-dependent reaction. And right up there near the top, you have a little bit of nitrate. But since nitrogen itself is not involved in most chemical equilibria involving nitrogen in the environment, there are some exceptions, but for the most part, the chemical transformations that happen within organisms that are metabolically driven don't involve N2, they involve exchange between nitrate, nitrite, ammonium, and ammonia. So if we plot up nitrogen without the N2, we get this diagram, which shows us again the PE conditions at which nitrogen goes from its most oxidized to its next most oxidized to its most reduced form. And again, what we anticipate to find in environments is going to be as a function of those transitions. Here's sulfur, which we've already talked about. And I also just want to mention carbon on this diagram. You can see the acid-base reactions between carbonic acid, bicarbonate, and carbonate ion. And the transition where we go to make methane, methanogenesis, happens at very low PE, very reducing conditions, even lower, even closer to the line than the sulfate-sulfide transition. So when we have natural environments that are making methane, it's really reducing. And the organisms that are generally driving that, and it's not only done by organisms, it can also be done abiogenically, but when it is, these are done by organisms that are adapted to live in extremely reducing environments. Okay, so that brings up this next idea, which is who's doing all that? Who's doing these oxidation reductions? And it turns out it's consortia of microorganisms, and microorganisms, it may not necessarily be one, it may be groups of them, and in different settings and in different environments, we may find different microorganisms. For instance, high temperature settings in geothermal systems may have different consortia of organisms and organisms we would find deep in groundwater, where the pressure is very high and the temperature isn't, versus things that we may find in the LOI canal, below the surface when exchange with the atmosphere and mixing is limited, or what we might find in a flooded soil. There's different organisms, but because of the commonality of the oxidizing and reducing agents that are involved, there have been metabolic strategies developed over life history on Earth that are pretty common, that involve various redox couples, that when we're in the presence of oxygen, that's the kind of respiration we have. Oxygen being decomposed to hydrogen to water so that we can digest organic matter. But when the oxygen goes away, the next most common thing we find is what we call nitrate reduction, which can first be nitrate to nitrite. Then we have nitrite reduction, which is nitrite to ammonium. Manganese reduction, its common oxidized form is +4, its reduced form is +2. Then iron, as iron +3 is an oxyhydroxide to iron +2. Sulfate to sulfide, CO2 to methane, hydrogen ions to hydrogen. They've been drawn in this order on this diagram of EH to show you that as we migrate away from the atmosphere, we move down, various reactions set or poise the PE of the system. And so these are common poise values that we find because one or another one of these reactions is governing the availability of electrons, which is affecting how every other chemical in the environment behaves. It's generally not the case that we can do this and this at the same time. We do them in sequence because they are done by organisms, and the organisms are adapted to live in specific sets of conditions, and there are very few microorganisms that do this reaction that can live in the environment where this reaction is also happening. So this sets up the concept of something called the redox ladder, which is a series of predicted values that we expect as we titrate organic matter in the environment. If we have an environment where it's in equilibrium with the atmosphere, we're never going to move away from this poise value. But if we're in any environment that's isolated from the atmosphere, it's going to have a finite amount of oxygen. And when we use up that oxygen, we're going to jump down to a new EH value and start doing another chemical reaction if the microorganisms and the reactants are present. Not all of these reactants are present in all environments. So this is from your text. It's a really simple diagram. It just has across the bottom weight of organic matter per unit volume, meaning just start with whatever, a gram of organic matter and some concentration of oxidant, some concentration of oxygen and nitrate, and in this case, sulfate. So only plotting 3 of these things on here. And you'll see that as organic matter is being decomposed by respiring organisms, the oxygen will go down. The sulfate won't change because the things that are going to do this to this only happen at much lower PE. Okay, now you see the nitrate, instead of being flat, it actually goes up a little bit because if the organic matter we put in there was algal protoplasm or any other photosynthesis produced material, there's a little bit of nitrogen in there, and as it gets decomposed, it will liberate a little bit of nitrogen, so it goes up. But as soon as the oxygen goes down, we're going to jump to a new PE value, and nitrogen is going to go down. So the nitrate that we see is going down. If we wanted to plot nitrite, we would see it going up because it's the product. And then at some point that gets used up. And in this particular example, it's an environment that doesn't have any manganese or iron reduction going on. So we jump all the way to sulfur, and then we see sulfur as sulfate going down. And again, we could plot sulfide, we'd see it going up. So that is basically how redox works together. This is a slightly more sophisticated way. Again, amount of organic matter reacted, arbitrary scale. This means going from no organic matter reacted to a lot. And over here we have PE values. And again, you can see some more of those poise reactions. Oxygen going to water, manganese oxide going to manganese reduced, iron oxide to reduced iron, sulfate to sulfide. And then along this pathway of methanogenesis, there are other reactions as well that collectively are called fermentation. So during this reaction, there's some cool chemical transformations that happen, such as for manganese and for iron, when they're in their oxidized form, they're not dissolved. But when they're reduced form, they are. So we can look at the very presence or absence of manganese or iron in the reduced form and say something about, oh, what's the oxidation state of that environment? Because if we haven't reached that level in the redox ladder, right, if we're somewhere up above here, we don't expect any dissolved manganese. We got to get all the way down here to start seeing dissolved iron, reduced iron. So that chemical transformation is really important. There are some other kind of solubility relationships that are shown here there that aren't necessarily quite as intuitive as present or absent. But for instance, the solubility of sulfide is highly dependent on the presence or absence of other chemical elements that like to combine with, which all sit over here in this part of the chart. Things like lead and cadmium and silver and gold. When we have them present, if sulfide is produced, it goes in with that stuff and makes minerals. Zinc is another good example. Whereas if sulfide isn't present, then it stays free in solution and can do other things. So we have 3 categories of terminology that we consider environments as being. If they are doing aerobic respiration or nitrate reduction, we call them oxic environments. We call them suboxic if manganese or iron reduction is happening. We call them properly reducing if SO4, sulfate reduction or CO2 reduction is happening. So in methanogenesis, interestingly enough, if you think about this for a second, we're pretty wasteful organisms. We spit out CO2 as the product of oxidation of organic matter. There are other organisms that can take our waste product and use that to make methane and therefore decompose more organic matter, but only at conditions of very low PE. Now, many people, including myself, just learn this as oxidized and reduced without these 2 subheadings. And if you refer to it that way, it's correct. But this gives you one extra level of definition, which is to say that, very oxidizing, very reducing, somewhere in between. This is just another version of the redox ladder, plotting the reaction progress of our unit amount of organic matter, the concentration of various chemicals, and how redox potential changes from high on this side to low. And again, those diagrams, those lines go up and down as a function of 2 things. The kind of consumption by the half reaction for being the electron receptor, as well as other chemical things that might happen in the environment. So for instance, you can see iron 2 go up and it goes back down again. And the reason it goes back down again is because when we get to the point where sulfate turns into sulfide, the sulfide is going to combine with the iron to make pyrite, and you're going to get pulled back. So the other thing I kind of want to emphasize is that metabolically speaking, it's rare to find that just one of those half reactions is what's actually happening in the environment. There are organisms that are affecting all sorts of electron transfer reactions. We do them all the time. Every time you breathe in and breathe out, you transport oxygen or CO2 from your lungs to the blood and back and forth. That's an oxidation reduction reaction on the iron in the heme, and various other things that we do to metabolize food, for instance, so that the amount of impact we have on the environment and any organism has is the sum total of a bunch of oxidations and reductions. Some of them happen at such a small amount of reactant product that they don't have an effect on the absolute value of the oxidation state in the environment. Some of them do. So some of the major ones are written out here as oxidations and reductions in the kind of typical ranges of PE that they exist over. And you can see here that some of these individual reactions can be combined together and given different names. I only show this to you, not because I want you to memorize it, but I want you to recognize that this is a fairly complicated and sophisticated system that involves organisms. Organisms have all sorts of other things that control how fast they metabolize, how many of them are present, how they vary as a function of environmental conditions like temperature and pressure and substrate availability, which we'll review next time. But that when we find values in the environment, we have to think about these values are actually being set by organisms. Okay, so I just want to now just spend a little bit of time giving you some redox ladder examples. There are basically two ways that you can go down the redox ladder away from oxic into suboxic and beyond. One of them is just you don't got very much oxygen, right? Things that are isolated from the atmosphere. Good examples are groundwater. Another one is that you got a lot of organic matter, dissolved organic carbon, particulate organic carbon, sewage outfall, swamps, you know, those kinds of situations, very organic rich, eutrophic lakes. Both of them have the same net effect in that they go down to oxygen decomposition and therefore reducing settings, but one of them can get there with very little organic matter, and one of them requires a lot of organic matter to get there. So this brings up another term. Maybe you've heard this before, maybe not. I use it all the time, so please do memorize this. BOD stands for biological oxygen demand. It means if we have an organic matter content in an environment, if it's present, respiring organisms are going to try to decompose it. That's just a given on Earth. And so therefore, the more organic matter, the more oxygen is required to consume that organic. We can have our BOD exceed the amount of oxygen in the environment, and in that case, we go down the redox. If somehow our BOD, it could be high, but as long as we can keep putting more oxygen in from the atmosphere, we won't go down the redox. That's really the primary difference. So BOD is an environmental parameter, which really means how much organic matter is there relative to how much oxygen. So here's an example of a stack of sediments. We're up in the water. This water might be exchanging with the atmosphere. This might be a lake. There's organic rich sediments in there. And so plenty of oxygen in the water. We start to pile up a stack of sediments. The sediments tend to have relatively low porosity, meaning relatively low spaces between the grains, and compaction tends to make those spaces go down as we go down. So the proportion of water to sediment goes down dramatically at the water sediment interface, then it continues to decrease from compaction. And because the processes through which water can flow through sediments are relatively limited, we tend to limit our oxygen resupply from above. Many cases have organic rich sediments. So with this interface, we go from being a place with sort of unlimited oxygen to limited oxygen. In the presence of a lot of organic matter, as we go down in various layers, we can see ourselves going down the redox ladder as the oxygen is consumed. So here's an example of what we might measure in some sediments. You can see depth in sediment in centimeters, nitrate, manganese, and iron, right? Nitrate's going down because of nitrate reduction. That means that the oxygen is already consumed, nitrate's going to nitrite. Manganese doesn't do anything until we get a little more than 20 centimeters down, and then starts to go up. It's going up because of manganese reduction. Manganese plus 4 as an oxide is not soluble, so we see it as 0. But as soon as it becomes soluble, because we've gone down the redox ladder to the point where we can reduce manganese, we start to see it increasing in concentration. Now, it's not a step function because of diffusion, which is something we'll talk about later. That's why we see a gradient instead of a step function. And the same thing with iron. The reason that we see iron becoming soluble at a deeper depth is because the redox potential for this transformation happens lower than that. And that's something you can convince yourself by going all the way back to this diagram, right? Iron reduction happens at a lower electrode potential than manganese reduction. They're not going to happen together. We're going to see one, then the other, and we see that in that stack of sediments. Here's another example. This is a soil that's being saturated. This is time and days, right? So you saturate the soil, and it's organic rich. We're not able to exchange with the atmosphere, so the water is oxygen limited. And you can see that within a day, the oxygen goes down. Within a couple of days, the nitrate goes down. We can see that over time, the dissolved iron is going to go up. We also see manganese given here as solids going down. All these things are predicted by the redox lab. And you can see the values of PE measured in that soil kind of going down over time. So this is an example where the redox ladder is applying not spatially, but temporally. There's another example. We have a couple of waste streams. We could have a landfill in the upper diagram, or we could have a leaky subsurface sewage transfer pipe in the bottom example. In both cases, they're going into a moving body of water, which is affecting from whatever this is, right to left, no, left to right, across the diagram. And what we see is that as we move up towards the contaminant from out fresh water, we go down the redox ladder, right? So we have oxidizing conditions, and then we get to manganese and nitrate reduction, iron reduction, sulfate reduction, methanogenic conditions. This is lower and lower PE, and any other contaminant or chemical in the environment that has a PE sensitive transformation is going to behave differently depending on which zone we're in. And part of the reason that we have this kind of gradient of conditions is a combination of concentration of reactant products as well as mixing back in from the atmosphere. Think about ejecting off from the side. This is a very two-dimensional situation, but we could bring in fresh water with a little bit of oxygen, and as water is flowing down, it starts to mix with that stuff. And we'll talk about how this process works in detail later. But in either of these cases, you can see that the redox ladder conditions exist and get more intense or more reducing the closer we get to the organic contaminants. This is just another example of a similar situation with a spill and the measurement of different chemical couples and the some kind of remediation situation, which is to drill a bunch of wells and just inject a bunch of oxygen. You can help prevent this from happening if it's something that's tractable in size. Final slide. One final thing I want you to think about is that when we do one of these kind of redox ladder calculations and we titrate some organic matter, we also change pH. So it's not just a function of PE changing. Some of the oxidation reduction reactions that we've written out consume hydrogen ions. Some of them produce hydrogen ions. So for instance, oxygen going to water, that makes the pH go lower. Respiration produces hydrogen ions, makes the environment a little acidic. Nitrate reduction has no effect on pH. Manganese and iron reduction actually go in the opposite direction. They consume hydrogen ions, they drive the pH up again. And then sulfate reduction has very little effect at all. So that if we were to go through one of these redox ladder titrations, we may end up actually, even though aerobic respiration makes environments acidic, at the end we may end up a little bit more basic. And this is just an example of a calculation using a set of parameters. And so this is always true that when we migrate down the redox ladder on a PE-pH diagram, we don't necessarily just move vertically. We can zigzag around depending on the relative proportions of these products. So we'll leave it there and ask if anyone has questions about environmental oxidation reduction. Please view that video if you haven't viewed it already.
You constantly do this Thursday?
We do not on Thursday. We have a video on Thursday, and then next week's videos as well. And then back to the week after next week.